All right, good afternoon, everybody. Welcome back to 6004. I'm Silvina Hanona-Walkman. I didn't quite get a chance to introduce myself last time. Today we're going to be continuing our discussion of the RISC-V Assembly, and we're also going to go into some binary notation, some of which you should have done in your recitations yesterday, but we're going to take it a little bit further today. But before we get into that, let's just review a couple quick things about course mechanics, since we went through it kind of quickly last time. So the website is 6004.mit.edu. Hopefully by now you've all visited it. If you haven't, then please do. There you'll be able to find lecture slides, tutorial handouts, practice quizzes, videos, the labs, everything, as well as direct links for Piazza, for our help queue, and also for submitting your labs and all that. So make sure to take a look at that. Also, just in response to my next bullet, which is Piazza, a lot of you did go ahead and join the class. If you haven't, again, please join, because we actually make some announcements on Piazza, and certainly lots and lots of questions are answered there. So I just want to make a couple high-level comments about Piazza. First thing is, every question is a good question as far as we're concerned. So if you don't mind, try to post publicly, because generally your friends or other people in the class are going to benefit from your questions as well. If you really feel uncomfortable, you're always welcome to post anonymously. And then if the problem really just pertains to you, then you can always post to us privately. The other thing is that often people ask questions that have been asked before. So we do ask, especially as the term goes on, to do a quick search for what you're looking for before you post another time to Piazza, just to save us some time. And I guess that's it about Piazza. And then the last thing I wanted to mention with regards to course logistics is that we really have kind of two things that play in parallel in order to really get the material across in this class. And so we have our tutorials where we go through sample problems often that try to make clear the concepts that we're teaching in lecture. We will sometimes do other things like talk about details of blue spec or things like that in recitation, but the main point is that the types of problems that for the most part you're going to see on quizzes are going to be things that we're going to review in tutorials. So very important to attend those. Then separately from that, we have our assignments, which are our labs. And so the labs are where you're really going to learn how to build this hardware, and it makes up about half of your grade. And so those two pieces really work in concert with each other, and it's important to realize that they're different, but ultimately they help to complement each other. All right, any questions? Great. So, back to where we started last time. So we talked last time about the components of a microprocessor. So we have three main components. We have a main memory, we have a register file, and we have our ALU, or arithmetic logic unit, which is doing our computation. And we saw that the way that the ALU works is that in order to do, what it does is it just gets its source operands from the registers. It never talks to memory directly. And so it'll read two source operands potentially from the register file, compute something, and then store the result back into the register file. And in addition, we have communication that allows us to bring information back and forth between main memory and the register file. So just keep in mind, and we're going to get into the details of exactly what this looks like for the RISC-V, but at a high level, remember that the main memory is really, really large and has enough room to store absolutely anything you need to store, but as a result of it being so large, it's slow. And the register file is very fast, but in order to keep it fast, we can only have a small number of registers. And so when we talk about assembly, the assembly instructions that we're going to learn today really directly show that this is what the processor architecture looks like. All right, so the instruction set architecture is, it's basically a contract between the software and hardware, and it specifies exactly what it is that your hardware is going to provide. So it's going to tell me all of the operations that my processor can do. It's also going to tell me the exact, details of what storage I have available. And it's going to tell the software how to basically make use of this hardware. And so as we mentioned last time, the instruction set architecture that we're going to work with in 6004 is the RISC-V ISA. Now, there's lots of different variants of the RISC-V. If you look out, on the web, you'll find that there's different data widths. So there's 32 bits, there's 64 bits, there's 128 bits. There's also an integer version versus there's additional support for floating point. There's also some versions that have extensions for multiply and divide operations, and so on. In this class, we're going to focus on the basic one, which is the 32-bit integer RISC-V. Okay, and that's what we're going to be building. All right, so as we said, the instruction set architecture has to tell you precisely the details of your storage as well as your instructions. So let's start with the storage, okay? So we already know that we have a register file and we have a main memory. Now we're going to get more specific about it. So for the register file, we know that the RISC-V has exactly 32 registers, and the data width is 32 bits. So we have 32 registers, each of which is 32 bits wide. And it turns out that it's very, very useful to have easy access to the constant 0. And so the X0 register is hardwired to the constant 0. So anytime you read the X0 register, you're always going to read a 0. If you try writing to the X0 register, it's as if you didn't do any operation. All right, what about our memory? So our memory is also 32 bits wide. And we call that one word. So everything that we're going to be doing in this class is going to be dealing with 32 bits at a time. So anytime we do a load or store operation from memory, we're fetching 32 bits at a time. However, a little slight complication, which is kind of more historical than anything else, is that the addresses which specify which location in memory we're trying to access are in terms of bytes. So what's a byte? A byte is 8 bits, whereas our word is 32 bits or 4 bytes, okay? So if we look here on this top row, you'll see that basically, 1/4 of our word is at byte 0, then byte 1, then byte 2, then byte 3, and so on, which means that our next word starts at address 4, okay? And so last time we kind of just glossed over this point of why addresses of consecutive locations differ by 4, but that's the reason. In addition, our addresses themselves are also 32 bits wide, okay? So if I have 32 bits of address, then what that means is that I can specify 2 to the 32 different possible addresses. Now, these addresses, remember, are in bytes, and so what that means is that I can specify 2 to the 30th different word locations, okay? So this is really a large memory. And you'll actually see later on in the course that we actually can supplement this memory with even further backup storage, but we'll get to that. Okay, so we've talked about what our storage looks like. Now let's talk about what our instructions look like. So we have 3 types of instructions. We have instructions that do computation. This is done by our ALU. We have loads and stores, which bring data back and forth between our main memory and our register file. And we have control flow instructions, which allow us to change the order in which we're going to execute instructions. So by default, we always execute instructions in sequence, one after the other, unless we hit one of these control flow instructions, in which case, you might jump to some other location in your program, and this is how we handle conditional statements and loops and things like that. Okay, so now we're going to get into the actual details of all of the instructions that are supported by the RISC-V, and don't worry about understanding or memorizing every single one of these. You're going to get very familiar with them through this lab that is going to be handed out today, as well as the one from next week. So you'll get lots and lots of practice with it, and also in recitations. And in addition, we will provide you with a short summary of the subset of the RISC-V instructions that we use in 6004. So it's easy to reference. All right, so what kind of operations do our ALU handle? There's actually 4 different things that it handles. It can handle arithmetic operations, which are things like add and subtract. It can handle comparisons, which can allow you to do something like check is, x less than y. And if so, do something with that. It has logical operations, which are things like logical and or. And then we have shift operations, shifting our numbers to the right or to the left. So we said that the way that the ALU works is that it gets both of its source operands from the register file. So it has 2 source operands, which are registers, and then it has 1 destination register, which is where the result is going to go. And it's okay for these registers to be repeated. In other words, I could have both sources and my destination all refer to the same register. That's not a problem. And this is the exact list of operations that are supported by the RISC-V. It seems kind of small, but you'll find that you can basically do everything with these instructions. So let's just quickly go over what each one of these are. So on the arithmetic side, we have add and subtract. The comparison, this stands for set less than and set less than unsigned. And so what this means is it's going to do a comparison between 2 things. And if the comparison is true, it'll set your destination register to 1. If it's false, it'll set it to 0. Logical are basically bitwise logical operations. And finally, our shifts, these stand for shift logical left, shift left logical, shift right logical, and shift right arithmetic. And we're going to learn in detail what each of those mean in tutorials. All right, so what's the format of our instructions? The format of the RISC-V instructions is always the operation, well, I should say 95% of the time. It's the operation, then the destination register, and then your source operands. Okay, so it looks like operation, destination register, source operand 1, source operand 2. Okay, so if I say add x3, x1, x2, the meaning of that is that I'm going to take the contents of x1, add it to the contents of x2, and store the result into x3. If I do a set less than operation with the same registers, it's going to compare x1 and x2, and it's going to say if x1 is less than x2, then I'm going to set x3 to 1. If not, I'm going to set it to 0. Now, one little caveat about this set less than instruction is that you're just setting it to 0 or 1, but the registers are actually 32-bit registers. So you want to keep in mind that the top 31 bits of this number are going to be zeros regardless of which direction your comparison went. It's only the bottommost bit that's going to change. All right, and then, if we do an AND, we're basically going to do a bitwise AND between register x1 and x2, and then we're going to store that into x3. And finally, here's one last example, which is shift logical left, and we're going to see a couple of these actually implemented with some examples. But basically what this is saying is take x1, the contents of x1, shift it to the left by the value that's stored in x2, and then put the result of that into x3. Okay? Any questions? Yeah?
What's the shift less than unsigned? What's the difference between the two?
There's no shift less than it's a set less than unsigned. And so that means that the comparison that you're doing, we're going to learn today about, we can have numbers either just all be considered unsigned, which means you kind of treat them all as positive, or you can have numbers that represent both positive and negative numbers. And so it compares them differently depending on which one it is. Any other questions? Yeah?
What do you mean by shift one value by another value?
I have an example coming right up in the next slide. Let me know if I don't answer it after that. Anything else? Great. Okay, so all of the values in our processors, we said, are binary, right? So everything is expressed in terms of zeros and ones. And you saw in yesterday's recitation a bit of a glimpse into how do we represent things in binary and how do we convert a decimal number into a binary number, at least for an unsigned positive number. So suppose that I have two 5-bit quantities. I have x1, which is 00101. Who can tell me what that's equal to in decimal? What's that? I hear 5. Can you tell me how you got to 5? Well, so I'll show you. So if I have 00101, the least significant bit corresponds to the power 2 to the 0. The next one is 2 to the 1. The next one is 2 to the 2, and so on. And wherever I have a 1, I actually have this value. So I've got 2 squared plus 2 to the 0 equals 5. Yes? All right, so what's the value of x2 in decimal? 3, great. All right, so if I add 5 to 3, I'm gonna expect to get an answer of 8, right? So let's see how I actually do that in binary. So here are my numbers in base 2, and just like we add in decimal, where we start with the least significant digit and move our way up, including carries, we're gonna do exactly the same thing here. And so we're gonna start off adding this 1 to a 1, and in binary, when you have a result of 2, that's equivalent to having a sum of 0 and a carry of 1, okay? So just like if I was adding in decimal 9 plus 1, I would get 10, meaning a bit of 0 plus a carry of 1, okay? So that's equivalent in binary. Now, once again, I'm adding 1, 0, and 1. Again, I'm going to get a 0, carry a 1. One more time, I'm going to get a 0, carry a 1. This time, I'm adding 1, 0, 0. So I just get a 1, and finally my most significant bit is a 0. And what is this equal to in binary? It's 2 cubed, which is 8, so everything looks good. Any questions about that? All right, great. So now let's take a look at the shift, which is what you were asking about. So suppose that I have this number x1, which is 00101, and I'm going to shift it by the number of positions specified by x2. So what this is saying is I'm going to take this number and I'm going to shift it to the left by 3. So how does that work? Well, first I'm going to shift it to the left by 1. So you just see that the number that I had here just moved over to the left by 1 position, and I put in a 0 in the least significant bit. Then I do it again. Now I have 2 zeros at the bottom. Now I do it a third time. Now I've shifted my number by 3. Now, one thing that's important to realize is that the width of my number didn't change, right? So the third time that I did a shift, you'll notice that this most significant bit, that 1, just got thrown off the other end of my number, okay? And so this is a very important concept, which is that in the computations that we're doing, our the size of our numbers are fixed, okay? And so if, for example, I was to add two numbers that result in a number that's larger than what I can represent in those number of bits, then I'm going to get something that's called overflow, which we're going to talk about in a second. And in fact, the answer that I get is not going to be correct. So specifically, let's talk about let's say that I was trying to add 3-bit numbers, right? And I did, I wanted to add like 1, 0, 1, and 3, but represented as 3 bits, right? If I added this in binary, I'd get a 0, carry a 1, 0, carry 1, 0. Uh-oh, I ended up with an extra bit, okay? And why is that? It's because I can't represent the number 8 using 3 bits of binary, okay? So generally what we do is we actually uses modular arithmetic. And so what we expect to happen is, in fact, that this would have given you the answer 0. Okay, and so why does that make sense? It's basically what you're getting is always the operation you were performing mod 2 to the n. Okay, so if I do 5 plus 3 mod 8, I expect to get 0. Yes? Any questions about that? Good. All right, so visually you can kind of think of it as numbers going around a circle, where if I had this example of 3 bits, I start off with 0 being represented as 0, 0, 0, then 0, 0, 1, and I keep building up my binary number all the way until I have all the bits being 1, and that represents the largest number that I can represent, which is 7 when I have 3 bits. Okay? So what does it mean to do arithmetic that's modular? Well, if I'm adding, it's kind of like I'm going around the circle in a clockwise fashion. If I'm subtracting, it's like going around the circle in counterclockwise. So suppose that I want to add 6 plus 5. Now, I can't represent the result of 6 plus 5 using just 3 bits, right? But I am going to get the result that I'm expecting, which is that 6 plus 5 is 11, mod 8, I'm expecting the result to be 3. And so let's take a look at how that works. I start with the number 6. I'm adding 5 to it, so I go around the circle clockwise by 5 positions, and sure enough, I end up at 3. Okay? And that's basically how our arithmetic in binary is going to work when we work with fixed size numbers. Okay, now you're going to find that as our numbers get larger and larger, it's going to be very, very tedious to write everything with just zeros and ones. And so we also have this notation called hexadecimal, which is kind of a shorthand, and it's instead of being base 2, it's base 16. But everything is still done in binary. It's just that we write 4 bits as a single character. Okay, so what does that mean? It means that if I was to have 4 bits of binary, which are all 0, that corresponds to the hexadecimal character 1. If I was to have, for example, 0, 1, 0, 0, that corresponds, as expected, to the decimal 4. But as soon as I go off the end of my decimal numbers, so 1, 0, 0, 1 corresponds to 9, 10 I basically label as the character A, then 11 is B, 12 is C, and so on until F, which is 15, which is the largest number I can represent using 4 bits. Okay? And so if I have this large number over here, which is 12 bits of binary, and it's kind of hard for me to look at and reason about, I can write it in hexadecimal as these bottom 4 bits are a 0 in hexadecimal, the next 4 bits are a D, and the next 4 bits after that are 7. And so another way of saying this is that the binary representation, which we show with this prefix of 0b, is equivalent to 7d0 in hexadecimal representation, which is shown with this prefix of 0x. Okay? Pretty simple, just a lot easier to deal with once we get to large number of bits. Okay, so until now, we said that our computational instructions always get its operands from the register file, and that it's reading two source registers in order to get the values. Well, it turns out, if you do some benchmark testing on all sorts of different applications, that when we write programs, it's extremely common for us to want to do computational operations where one of our source operands is a constant, like a small constant. So, you know, I might do x plus 1, or I might do I minus 1 as my, you know, to decrement a loop, things like that. And so it's so common that we actually make special instructions for this, so that instead of having to load these small constants into a register and then operate on two registers, we actually have operations which can deal with one register and a small constant which is encoded into the instruction itself. And so what does that look like? Basically, it's just like we saw before, except that now instead of having a second source register, we have the small constant that comes directly from the encoding of our instruction. And so here are, you know, the same examples we saw before, except that now I have a hard-coded constant 3 rather than a different register being my second source operand. And if we look at all of the register, we call these register immediate type of instructions, we basically have essentially the same list of instructions that we had in the register model, except for one tiny difference. Who sees the difference? Which instruction do we not have in the register immediate? Yep. Subtract. Why do I not have subtract? Exactly. So there's no need for a subtract instruction. So you'll see that in general, when we're building these instruction set architectures, they're minimal in order to try to keep things simple and to make the hardware as simple as possible. So if you have two ways of saying the same thing, you're going to, for the most part, not create a second instruction for it. Okay, and so instead we would have an add I with a constant of minus 3 if what I wanted to do was x1 minus 3. Okay, now what about this expression, right? I mean, in Python or whatever programming language you have, you can imagine, you know, writing something like this where you add something, you shift it, you know, then you subtract 1. Oh, sorry, yes?
What counts as small for the immediate?
12 bits, and I'll get into that later in the lecture, okay? So suppose that I wanted to, right, execute this instruction, right? Even if I had all of these values, you know, the B, the C, the 1, and the 3 in 4 different registers, I can't actually write an assembly instruction that can execute this operation as a single instruction. So instead, what I have to do is I have to break it up into smaller components where each one is just doing one basic operation, right? And so how would I actually implement this? You can, you know, break it up basically by the parentheses. So the first thing I'm going to do is I'm going to add b plus 3, and I'm going to store that into some temporary register. Then I'm going to take that result that I produced, I'm going to shift it to the right by c, and finally I'll take the value that was the t1 that was produced from that shift and subtract 1 from it in order to get the final answer that I want. So what does that mean? If I'm trying to write this in assembly, what that's going to look like is, let's assume, you know, that my variables are already in the registers listed here. And so I'm actually going to have, you know, 3 different assembly instructions in order to execute this one statement in my high-level language. Okay, so just keep that in mind, that you have to break things up into smaller components when you're writing your assembly. Okay, now we're done with the computational instructions, and so we know how to do, you know, any kind of compute high-level instruction at this point. So now we're going to move on to control flow, right? Suppose I had the statement right here, which is if A is less than B, then set C equal to A plus 1. Otherwise, set C equal to B plus 2. So what's happening now is that I'm no longer going to execute my instructions in sequence. So in order to do that, I have to have some way of deciding whether to switch to branch to a different location based on some conditions. So we call this a conditional branch. And the structure of the assembly language for the conditional branch is that you're performing some comparison on source 1 and source 2, and based on the result of that, if the result is true, then you're going to jump to label. Otherwise, you're going to continue execution of your code in sequence, okay? And here in this table, we have the list of all of the comparison operations that are supported by the RISC-V, okay? So what do these shorthands stand for? BEQ is branch if equal, BNE is branch if not equal, BLT is branch less than, branch greater than or equal to, and then the other ones with a U at the end just means an unsigned version of those comparisons. Okay? Now, you'll notice that there are certain comparisons that I don't have here, right? Like suppose that I wanted to, instead of doing less than, let's say that I wanted to implement, I wanted to, you know what, I'll get to that example in a second. Let's first translate actually this if-then-else statement, okay? So you'll see that the first instruction that I show here in my translation is branch greater than or equal to rather than, you know, BLT. Why is that? If my if statement says A less than B. What am I doing? Yes?
If you want to jump to the else if it's greater than or equal.
Exactly. So if it's less than B, I don't want to take the branch, which means I have to figure out what the, you know, the reverse of that comparison is. And so I want to take the branch if A is greater than or equal to B. Okay? And so that's what this BGE instruction is saying, is if x1, which contains A, is greater than or equal to x2, which contains B, then I'll go to this else, okay? If I don't go to the else, then I'm going to execute this next instruction, which is going to do my C equals A plus 1. And what is this instruction right here, BEQ x0, x0 end doing? Yeah?
So if A is less than B, then you want to skip the else.
Exactly. So if I say, you know, is x0 or any other register for that matter equal to itself, the answer to that is always true, meaning that I'm basically writing an unconditional branch. And so I'm saying, once I've executed this instruction, I always want to go to end in order to not execute what's at the else label. Okay? Any questions about that? Good. Okay, so those are conditional branches. Now, just like we have conditional branches, sometimes we want to jump unconditionally. And so we have two kinds of unconditional jumps in our in RISC-V. The first is called JAL, which stands for Unconditional Jump and Link. And we're not going to worry today about what the link part refers to. That's going to come up in our next lecture on Tuesday. But the main idea is that you're not doing any comparison. You're just always jumping to this label. Okay, so jump and link, register, comma, label as the result of jumping to this label. Similarly, I have a JALR jump instruction, which is also an unconditional jump, except that the difference here is that instead of specifying my destination as this label, I'm going to specify a register which holds the address of the location that I want to jump to. Okay? Now, the benefit of that is that when when I specify a label, I have to encode somehow what that label is representing as part of my instruction, okay? So what does that mean? That when I have a label, I'm actually storing in my instruction an offset of from where I am right now to how far it is to get to the destination instruction. Whereas if I want to take, you know, a huge jump that would go, you know, past lots and lots and lots of instructions, I might not be able to represent that using the small constant that's embedded into a single instruction. And so instead, I have the ability to put a large value that's up to 32 bits into a register, and then I do an unconditional jump to the location pointed to by that register. Okay? All right, so now let's perform, you know, A is equal to B plus C. And in this example, we're no longer going to assume that A, B, and C have been brought into some registers, okay? And so now we're going to start dealing with the fact that actually most of our values come from memory, right? So in order to do the addition operation, I first have to bring B and C from my memory into my register file. So how do I do that? I'm going to do these load operations and store operations for writing my results back. Okay, so let's summarize what we've seen so far. We first did our computational instructions, then we had control flow instructions, which were the conditional branches as well as the unconditional jumps. And now we're ready to learn the last two types of instructions, which are load and store, which allow us to go back and forth between memory and our register file. Okay, so what do I have to specify when I want to get something from memory? I have to specify the location of where it's coming from. Okay, so if I want to get variable B, which is stored at address 0x4, I somehow have to tell, you know, the machine, get me the thing that's at address 0x4 and put that into x1. So what does that mean? It doesn't mean that it's going to put 4 into x1. What it's going to put is the value that's stored at address 4, which is this variable b, and that's what's going to end up in x1. Okay? Similarly, load 0x8 says take the thing that's at memory location 8 and put that into x2. Now that I have my values in my registers, I can add them, and I put the results into x3, and now finally I can take that result from x3 and store it back into memory, which means take the contents of this register and store it into this location, which is a location where variable A is being kept in memory. Okay? So, so there's a couple things to think about when it comes to loads and stores, which is that I haven't yet shown you the whole picture. So you might say, well, you know, why can't I say, you know, add memory location of 4 to memory location of 8 and store that into memory location of 10 directly as an assembly instruction, right? Well, let's think instead of how we do it and then why we might have to do that, okay? So when we do loads and stores, it turns out that it's very useful to specify it instead of as a hard-coded constant to have some kind of a base value plus an offset, right? So what is this good for? If I have an array, for example, I can store in the base address register where my array starts, and then I add to it, you know, the number of bytes that I need to jump in order to get to the appropriate element of my array. Okay? And so basically, my load and store instructions, the actual format of them in RISC-V is the following. LW stands for load word. And so I'm going to load word. This is a destination register. And then this is specifying the location of where I'm fetching the value from in memory. Base is a register, and so it's taking the contents of this register and adding this small constant offset to it in order to figure out the address. So if I go back to my example over here where I was actually fetching from address 0x4 directly, the way to actually write that in RISC-V is that I have to specify a base register. So in this case, since I don't want to actually add anything to the address 4, I'm going to specify x0, which is always equal to 0, as my base register. And so if I say load W x1, 0, x4, x0, the meaning of that is I'm going to load into register x1 the value that's coming from the memory location whose address is what's stored in x0 plus the constant 0x4. Okay? It's kind of a lot to wrap your head around, but as you get used to it, it won't seem so daunting. Any questions about that? All right, terrific. So if we get back to the program that we saw last time, we're now actually ready to understand all of the instructions that were needed in order to do, the sum of an array of n elements which are stored in memory. And so what we want to do initially in order to make this program work is bring some values from memory into my register file. And so specifically, I'm going to bring base into x1, n into x2, and sum into x3. And I'm going to assume that the address of where I can find this value of variable base has already been brought into some register. Okay? So how do I write this code? The first thing I'm going to do is I'm going to fetch that value of base. So where is base in my memory? What address is base stored at? 100. So if I have in register x10 the value 100, then what does it mean what address am I fetching by doing 0x0 parentheses x10? I'm fetching the address 100, okay? So I'm fetching the contents of x10 plus this constant. So that's 100. And so that's going to tell me go to memory at location 100 and bring that into register x1. Okay? So that takes care of bringing base into here. Similarly, I have, two more load instructions, which are going to bring my n and my sum from memory into my registers. And the way that I access them, you'll notice is I still use x10 as the base register because x10 is kind of representing, where are my variables starting to be specified in memory. And then I'm saying, okay, so my second variable I can find at x10 plus 4, and the one after that is at x10 plus 8. Okay? So this gives you an idea of how you're going to bring variables from memory into the register file. And then we have the loop, which we saw last time, which is basically taking the value that's pointed to by x1, which begins at a0, and it offsets it by 0. So it says, give me the value of that array element, and put it into this temporary register x4. Then I'm going to add to x3, which is holding my running sum. I'm going to take the current value of sum and add this value that I just fetched from memory. Okay, so the first time through, it's going to bring in a0 and add that to my sum. Now, this is the line we were missing last time, which is I'm going to make x1 point to my next array element. Okay? So how do I make x1 point to the next array element? I increment it by 4 because each element takes up 4 bytes. Okay? And so that's what this x1 plus 4 is doing right here. And finally, I decrement my count by 1 to indicate that I have 1 fewer thing to add, and I jump back to loop. Any questions about that? Terrific. Okay. Oh, sorry. And of course, the last thing is we're going to take our result and store it back into memory. Okay. So we only have a few minutes left, and a few things I still want to try to get through, and whatever we don't finish is going to be gone through in recitation tomorrow. But let's first elaborate a little bit on these small constants that we were talking about and what actually limits their size. Okay, so if my instructions are also a fixed width, they're 32 bits, just like everything else in our RISC-V, I have to be able to, gather a bunch of different information out of those 32 bits representing my instruction. Okay, so the first thing is I have to figure out, well, what's the operation that it wants me to do? Is it an add? Is it a load? Is it a million other things? And remember that we're only dealing with a very small subset of what the RISC-V can actually do. And so to encode that operation, we actually use 10 bits of our instruction to specify what operation it is that we want to do. All right, now the next thing I have to do is specify, let's think about our ALU operations that have two registers, two source registers and one destination register. How many bits do I need to represent each of those registers? How many total registers do I have? 32. In binary, how many bits do I need in order to represent the numbers 0 through 31? 5, exactly. So for each one of those operands, I need 5 more bits, okay? So I might have 5 bits, for one source, another 5 bits for the second source, and then another 5 bits for my destination. So you see very quickly that I'm running through these 32 bits very quickly, okay? So if we think about the example where we have one source operand and a constant, you'll see that the numbers are basically 10 bits for my operation, 5 bits for that one source operand, so that's 15, another 5 bits for my destination, so that's 20, so what do I have left? 12 bits, okay? So when I say small constant, we're limited by what can fit into our instruction in addition to everything else that we're already putting in there, and so that means we can only represent constants that fit, I'll be with you in a second, fit into 12 bits, a 12-bit encoding in binary. Yes?
Why do you need 10 bits for the operation? Now you find it close to 1024 operations.
I know, and so as I mentioned, we're really dealing with a very small subset of the RISC-V, and so there's a number of different reasons why they actually use a total of 10 bits. They don't use every single different encoding. They actually use some things to, to make it very easy for the hardware to say, okay, if my encoding begins with this sequence, then I'm dealing with register-register computations. Or if it begins with another sequence, then I'm dealing with register immediate. So there are a lot of things that are done in order to simplify the translation from the encoding into the hardware, which make us want to use more than the number of bits that would, you could actually directly encode every single operation into. But very good question. Okay, so, sorry I said that. So the one last thing I wanted to say about this is that this actually brings us back to what we were talking about when we were saying, what kind of memory operations are supported by our RISC-V instruction. Right? So we said that the way that we have to specify our memory instructions is that we have a base register plus some small constant, and that specifies what the address is from the memory location that we want to access. And this kind of, highlights why that's the case, right? If each one of my addresses in memory is 32 bits, there's no way that I could specify an operation plus 2 source, memory addresses plus a destination address all within 32 bits. Okay, and so we don't support instructions that say something like add memory location A to memory location B and store that into memory location C, because we have no way of encoding that into 32 bits. Okay? All right, so just to wrap it up, as I mentioned, you know, the instructions that are actually supported by the instruction set architecture are pretty minimal. They just are the instructions that you need in order to do everything that you need without going beyond that. But, you know, sometimes it turns out that it's easier for us to think about, you know, instead of branch on less than, maybe I want to do a branch on less than or equal to, even though officially that's not an actual RISC-V instruction. And so because we're always able to express that in terms of other pre-existing instructions, there is actually support for this in RISC-V, and we call these pseudo-instructions. And so they're basically an alias to another instruction that we already have support for. So for example, we have this very convenient move instruction, which basically just says take the contents of register X1 and put them into X2. Well, I don't need to create an actual new operation that does this, because I can simply do an add-I operation of X1 with a constant 0, and I get exactly the same effect. Okay? And so I've listed here a few other pseudo instructions that might come in handy as you write your assembly programs. And in the handout that we give you that lists all the 6004 instructions, we also include a listing of all the pseudo instructions that are available to you. Okay, so we're out of time, which is why we had this material at the end of the lecture. And so the one thing that we haven't yet talked about is how do we encode negative numbers, okay? And so that's actually going to be covered in tomorrow's recitation. But what's going to be introduced is a concept of 2's complement encoding. And once you learn how that works, you want to realize that all of our assembly instructions are always using this 2's complement representation to store any constants that it needs to make use of. All right, thank you very much. We'll see you on Tuesday.